My name's Mark Sofroniou. I work on numerics mostly. I'm going to talk about the runtime library. I'll describe what that is. I'll try and give you a little bit of an overview of what it does, and I'll spend most of the time talking about the things that we've been doing to develop it. Most of what I've been doing is with Ilian, who's sitting here in the audience too, so feel free to talk to either of us afterwards. So what is the runtime library? So several years ago, when the compiler was rebuilt, we moved a lot of functionality out of the kernel into a separate library. And most of the functionality that was moved out was data structures, mTensor, which is the heart of the packed array data structure, mSparse array, which is the machine sparse array data structure, and something new that was recently added is this mRaw array that you've seen probably if you've been to some audio talks or things like that. So you can support different data formats with different bit sizes, etc. It's the home of where most of the machine arithmetic, scalar, and vector operations live. The core linear algebra operations, the BLAS, basic linear algebra subroutines. There's also lots of other stuff, random number generation, hashing functions, hash tables, which don't have a user API, but we use a lot in the kernel. Thread-safe memory allocation, and threads for scheduling. Very, very low-level functionality that we don't really have APIs for users in the kernel, but which are used a lot throughout the computation of things. It's accomplished using a mixture of C and a growing amount of C++ code with some platform-specific optimizations and some special-purpose libraries. So I'll talk a little bit about those. The most significant libraries that we use are this math kernel library by Intel, mainly for linear algebra, some vector arithmetic, and we're also using this integrated performance primitives, vector arithmetic, and some image processing type of functionality. We use them in a mode where the results are, in a sense, the slowest mode that's provided because we want things to be reproducible from one session to another. We don't want any randomness in the results of things that are being solved. So we've added a lot of new operations from IPP. IPP adds a lot of functionality that's not in MKL for vector arithmetic. So some of the things that we've added, some trig and arctrig functions, vector norms, min, max, total, mean, and the list goes on. So if you do your operations using packed arrays in a vectorized kind of way, you should get some kind of fairly big speed up. I don't want to give you lots of plots and things like that, but I'd just say something like a factor of 2 for min and max, up to a factor of 7, with 4 being typical. So machine arithmetic operations in Mathematica check for arithmetic exceptions. When you type 1 plus 1, it's not just calling 1 plus 1 in a C routine. It actually has to check if that 1 plus 1 can fit into a machine integer. Okay? Every single time you enter an operation, Mathematica is doing work to see if the result that comes back still fits into the same type, or if it has to dynamically change the type of the expression and return a different result. So these functions are implemented inside this runtime library so that they can be shared when you compile code through the bytecode of the compiler, or if you generate C code even through a library, they can be shared between all these different functions and implemented and optimized in only one place. That's the important thing. So here's an example. If I just take a machine integer, the maximum machine integer, and add 1 to it, Mathematica returns me an integer, but this is no longer a machine integer. So this addition here was carried out in the runtime library. It said, your result has essentially wrapped around, no longer fits a signed integer, returns an error status from the runtime library, and then we go and do something in arbitrary precision. And a similar kind of thing happens in the compiler. If you compile that code and you try and add 1 to that number, then what you get is something like this error here. The numerical error was encountered at a certain instruction. So the flagging of this error came from this machine arithmetic function from the runtime library. Okay, so you can see a tiny snippet of the runtime library when you generate C code through the compiler. Okay, From that compile function that I had on the previous slide, if I use this C code string generate to generate C code from the compiler, right down here, tucked down here in this black line here, you'll see a call to some obscure function. I've omitted a lot of preamble code there. My thing doesn't work anymore. That's better. Okay. And this is the function that's called here. Okay, this obscure looking thing here. And this is the one that does the plus, the actual addition from the runtime library that's linked into your code. Okay. If I switch off the overflow and underflow detection and generate C code, then what I get is something that looks like this. It just calls the C function here. Okay. This is no longer using the runtime library. It's just calling the C plus function. Okay. So it doesn't do this additional error checking. It runs faster, but the downside is that you'll get a negative answer for the result. And you can get another glimpse of this runtime library when you compile stuff. The compilation target goes to C and use the old compiler to generate C code, compile it, link it to a library, and link that library back into the compiled function. If you look inside that compiled function, you'll see this library function. And this library function is living on the top of functionality that's built into this runtime library that we use. Okay. So let's look at what are the advantages. Well, this is a typical one. In a procedural type of language, you write something in an iterative way. You just sum numbers in a loop over and over again. Every single time you do some operation here, you're making data structures, and you're interpreting the operation. And there's a lot of overhead. You're having to go through the evaluator in Mathematica, etc., which you don't want to do it if you're doing a purely numerical computation. If you do things in a different way, here I make a packed array, essentially, which is an array of machine numbers, then I can use vectorized operations. So these vectorized operations total will be calling a vectorized operation in the runtime library that can go and sum up those things in a vectorized, very fast way. Okay. So that's where the efficiency comes from. So let's look at a little bit of the work we've been doing to improve parallel computation. Okay, in parallel computation, there are very different ways of scheduling jobs. Okay, I'm only going to look at vectors. So let's take a vector that has, say, 64 blocks. Okay, I'm going to chop it up into pieces. Each piece has eight blocks of computation in it, and I'm going to give those pieces off to a multi-core machine. So in an ideal world, with no communication overhead, what's going to happen is I should hope to be able to run 8 of my pieces of my vector on one core, another 8 on another core, another 8 on another core, and I get a factor of 8 speed up. Okay? And this is a very simplistic model that ignores overhead for scheduling, communication, and synchronization. But in the real world, an idle machine is good for benchmarking, but it's not really what we work with. Okay? We might be using a shared workstation, something on the cloud, or we might have other processes going on our machine, web browser, operating system, the front end of Mathematica. We might be compiling some code or something like that. So what I've done here is in my cores, my 8-core machine, these red blocks, this is a time sample. These red blocks are busy doing other operations. Okay? So I need to run 8 blocks on each processor, but some of the processors are busier than others. Okay? So this is a problem because the cost of the job is dominated by this busy core. Okay? And this is the kind of partitioning that's used for the vector operations in Mathematica 11. Now, the question is, why don't we often see such very bad behavior? Here we've only got a factor of 2 instead of a factor of 8 speed up. Okay? And the reason is that the operating system will often move some thread to another processor. Okay, so it kind of saves us from this worst case behavior, and it does it like this. When we're moving along here, we haven't done very much of this. Suddenly, another core becomes completely free because it's finished its job, And the work that was left here can be moved over here. Okay, so the operating system has rescheduled some work and moved it over to another core, and we've kind of got a much better situation than the one we had before, where it was dependent on the slowest core. Now, this is good, but it's also non-deterministic because there's no guarantee that it could have moved that particular thread to that particular core. It depends on the workload of the CPU and everything. So here's another scenario, and the running time is slightly different here. Okay, so it really depends on the operating system schedule, which cores are idle at which particular time, what the workload is, et cetera, et cetera, et cetera. So one of the things that we've tried to do is to use a more modern technique for work scheduling called setting up a work list and work sharing, or stealing as it's called sometimes. And the idea is that we'll just have a list of 64 blocks. We don't care which thread or which CPU handles each one of those individual blocks. We don't care. We just need to know whoever's free at whatever time is going to go and get one of those blocks and go and work on it. And if we do that, then you see that we can compactify all of the work to whatever's free at whatever time. Each thread, as it moves along, can take whatever block is next in the list of that vector computation to do, and it can go and do it whenever it's ready. As soon as it's done, it can go and get another block off the list. Okay, so, and then here, we see that some of the other threads took work that wasn't completed, that was originally tied to the first thread. So in a sense, we're freeing up one thread from doing work from another thread, okay? And we can get a much more reasonable speed up, much closer to the ideal of the factor of 8. And we don't rely on the operating system scheduling, moving our jobs around from one process to another. Now the challenge is, how big a block of work should we take? We take a block of work that's too small, then we're going to have a lot of communication overhead between these threads, and it's going to be more than the actual work that's done in the vector computation. If we take too big a block, we're going to be back to that situation where the slowest core was dominating the entire time of the computation. So what we've done now is we have in the new version of Mathematica something that's going to interrogate the processor on your machine, and that code is going to look at what kind of cache structure you have. And it's going to try and say, oh, the largest cache for your CPU divided by the number of cores is the amount of work that I'm going to try and use. That's my basic byte quantum. And so we select the block sizes according to the size of this cache per core. And the number of vector elements that's going to run in that chunk depends on the type of operation that we're doing. If it's an addition, it needs 2 vectors in the addition and a vector for the result. So we have 3 vectors worth of data to fit into that block. So the length of the vector being operated on is going to be slightly smaller. If it's something like total is just a single vector and accumulating a scalar. So we can use pretty much all of the cache for that length of vector. And another advantage is a slight improvement in cache locality. So just to show you, in practice, this is the new strategy that we have, and this is the old strategy that we had here. This is in a machine that had 16 cores. 8 cores were busy with jobs that someone else was running on the machine. So it's quite heavily loaded, this machine, okay? So you see that the new scheme can gain around 30% of execution time. And as a worst case, we'd expect, here I have a machine with 12 cores that's completely idle. So in the worst case, the old and the new strategy should be pretty similar, but that's not the case actually, because sometimes the operating system every so often does some kind of task. And so the new strategy, even on an idle machine, ends up being just as good. And the communication overhead you can see is just negligible here. So another thing that we've done is to look at machine integer instructions. So when we need to check for an integer overflow, something like multiplication, one integer times another integer, sometimes the only way to do it in C code is to go and divide the result by an integer to check that you haven't had a wraparound of sign. But that means you're doing a multiplication and a division for every integer multiplication. So that's more than twice the cost of the operation. Okay? So that's slow. We don't want to do that. A lot of compilers have what they call built-in or intrinsic operations that allow you to do that instruction and flag an error, saying it knows when it does this in its CPU die if there's been some wraparound or overflow, and it will return that as a bit flag. And so it's practically the same speed as just doing an integer multiplication. So if you can have access to that lower level functionality, you can get something integer multiplication or addition or subtraction at the same speed as if it was unchecked. So that's what we've implemented in the development version here. This is a machine with 4 physical cores. In the blue is Mathematica version 11, that's the execution time. In the orange is this platform-specific intrinsic compiler operation. So you get a factor of 2 here because you've avoided doing a multiplication and a division. It's pretty much a factor of 2. And the other thing that we've done is implemented on top of that a multi-threaded layer. So we have now machine integer blars that can run in parallel using compiler intrinsic optimizations. And we get up to a factor of 7 speed up here on a 4-core machine. So, how am I doing for time? 2 slightly controversial things that I want to go on to. This is very important for the new runtime that we're working on. So there's a new runtime for the new compiler, and it has different requisites than the runtime from the old compiler. So we're developing these 2 things. At some point, we're going to need to put them together. So there are some topics that we need to think about, how one fits into the other, and how we want to move forward. We want to use more modern tooling and software techniques for the new runtime. And we want to retool the old runtime so that eventually we can merge the 2 together. So one of the things we've been doing is looking at machine complex functions. In the more recent C standards, there are machine precision complex functions as part of the C99 standard. And that means we can get things with standardization of exceptions, more efficient, and we can also remove some of our own implementations of these functions from the runtime library. So here's an example of a good thing of this library. If you run this in Mathematica and you have the tangent of a complex number where the real and imaginary parts are the maximum machine number, you'll get an overflow. And that's because in our implementation, if you look at this form of how it would be implemented, we would see, in here there's an intermediary exponential that it's not able to fit into a machine number. But in the C library for this function, it has a special case for the asymptotics. And so it's going to say, well, I don't really mind if it's going to overflow or not, because I know that the numerator and the denominator are going to be the same size. So asymptotically, it's going to go to 1. Okay, and so in the new version of Mathematica, you'll get a machine precision result for that, because the C library function implementation had a special case that wasn't in our library code. A problematic thing, though, is when we come to inverse trig functions. Okay, so this is the current situation that we have in Mathematica. If I switch to C99, then I get this situation here. And you'll see, okay, all well and good, these are exactly the same. These look similar, but unfortunately, the sign of the real part is different. Okay? So the question is, why the difference? If I had a bit more time, I'd let you think about it and maybe come up with some ideas, but it's kind of complicated. Okay? The reason goes back to this paper from the 1980s called Much Ado About Nothing Sign Bit by Kahan, who's the grandfather of floating point arithmetic. And I've called it A Tale of Two Zeros, Dickensian version, if anyone wants something different. But basically, it all goes down to the fact that in IEEE 754 arithmetic, there are 2 zeros. There's +0 and there's -0. And just the difference that 0 can have a different sign to what it does in Mathematica can cause that difference. Now, we've mainly been using IEEE arithmetic for reals, and we've written our own functions, complex functions. So this hasn't been an issue before. But if the C99 library function suddenly is relying on this behavior of negative and positive zeros for its branch cut structure, you'll see here we have the inverse hyperbolic sine function. Okay, let's say that on this branch here, like we saw on the previous slide, Mathematica and the C99 function were the same. Okay, let's say that, okay, over here on this branch cut, they're the same value. Then by symmetry, if I take minus that value, so I flip it over here, in C99 code, I'm going to get a minus 0. So I'm going to flip from the branch being up here to the branch being down here. Okay? Because the 0 is negative. It's no longer positive. So the 0 inherits the sign of the negation. But in Mathematica, zeros always have the positive sign, so we'd end up over here, and that's the difference between the two. Mathematica, instead of going down here, would go up here. So this is a slight incompatibility, and it's something that we need to resolve if we're going to use these functions in a vectorized way. So another thing, just the last few minutes, is another thing that we need to discuss. So I've really thrown this out there because I want to know people's opinions. I mean, like, how horrible would it be if we introduced signed zeros in Mathematica? MATLAB, Octave, Python have them. Some users get very confused by them. I mean, it's a possibility. Do we want speed at all costs, or do we prefer to maintain, the status quo that we have at the moment? So these are the sorts of things I want to throw out there, I want to discuss. So another issue is moving forwards with this runtime library, pushing the boundaries, trying to make it faster and faster. What do we do with underflow? So underflow, if you take a machine number and you divide it by 2, then you get an arbitrary precision number. It no longer fits in the range of machine precision arithmetic. Now, unlike overflow, underflow needs to be determined for every single function. So arcsine, cosine, sine, or whatever. We need to look at the expansion of that locally around small values and determine whether it's going to underflow. And it was, a week or so of work to add it for these complex trig functions. Another thing is it causes a slight stalling of the processor pipeline when we do things in a vectorized way, because you have these if statements, if something's underflowed or not, and that causes kind of branch protection. It affects the kind of vectorization of the code as it's going through in the runtime library. Another horrible thing is underflow causes unpacking of packed arrays. So you have one number in your big packed array image or whatever, the whole thing gets unpacked. And we have situations already where underflow is always disabled, like when we solve PDEs in NDSolve. Now in NDSolve you have transient phenomena, you have things varying on a very different time scales, but often over a very short period. So suddenly something could underflow, but it's not really physically significant, okay? And if that suddenly caused your computation to slow down in that small region, at the end of the day, if it was 0 or if it was something very, very tiny, it doesn't really make a lot of difference. It doesn't affect the end solution. So we are paying a penalty for this. Here's another example. So let's take a cumulative distribution function. This is like a probability. Asymptotically, this probability is going to turn to 1. Okay, good. So if I compute it, for quite a large value, I get 1. But if I compute it for a much larger value, then I get a machine underflow. I go and compute something with arbitrary precision, and I get a result back. But now look, like this is smaller than 1. So what I have here mathematically is a non-monotonically, non-decreasing function, but like increasing the argument here, I get a smaller number. Okay, so mathematically, there's something not quite right there too. And apart from the speed, okay, this is just much, much, much slower. And the point is, in this context too, like in NDSolve, it's not really significant, whether the exponential of minus 1,000 was, some very, very tiny number or 0. Effectively, it's 0 in this particular context. And another thing is, when we were looking at these vectorized functions, some libraries don't really do underflow very well. it's not something a lot of people use. So we were using this IPP library, something Ilya and I found here, when we were testing. We were testing the square root, the vector square root function from this IPP function. So here's the minimum machine number. This is a half. This is 2. This is the maximum machine number. This is what you would get in C code, the square root of this number. But the maximum machine number here doesn't even have the first digit correct in the Intel library. Okay, and we're only using the Intel library with a mode that sets underflow, but it's affected the maximum machine number. Who knows why? So I mean, we have reported this to Intel. They weren't aware of it. It's been 3 months now. They're still working on fixing it. Okay, so these are quite esoteric issues. I mean, I'm not saying it's hard. It probably is a very hard problem for them, and they've been very, receptive and responsive. So I don't want to say anything like negative. I'm just saying that we are using things in supporting that functionality that are kind of pushing boundaries, and it's something we should think about. Another thing that we should also think about is like symbolic versus numerical evaluation. We do lots of transformations, traditionally in Mathematica, with a view of symbolic computation. So we do simplifications. We were talking about logs the other day, right? You enter log of x, y, and it evaluates to log of y divided by log of x. Okay, a similar thing for the square root. The square root can evaluate to a power of something to the half. And this is another common one. A division, or what looks like a division, is implemented as a multiplication of the reciprocal. These are vectors. This is 2 vector operations instead of us, doing it directly as a division. And also, different rounding properties. Each of these symbolic forms, once it's been expanded out, has a different numerical property. You might get here like something of the order of machine epsilon when you're computing a complex square root or something, an error introduced by computing using a general power instead of computing using a square root. And also here you might get something that's off in the last few bits because you're doing a multiplication. You have a rounding error from the reciprocation, and you have a rounding error from the multiplication. Let's skip that one. So I'm going pretty much over time, so let's just conclude here. The runtime library is the computational engine of the mathematical kernel and compiler. We're putting a lot of effort into developing it. We've improved some aspects of it, like thread scheduling for vector operations. We've added new optimized vector functions to improve performance. We're looking at compiler-specific things once they're widely supported in different compilers to improve performance. We're trying to use more modern things like C99 standards for complex functions. And at the same time, as we move towards this new compiler that we're developing or whatever, we also need to think about some issues that might be related to further developing and further pushing the boundaries of performance there. And one would be this issue about signed zeros. This issue of positive and negative zero in IEEE arithmetic that we don't have. We can't select which of the branch cuts we're able to choose in Mathematica because we don't have the possibility of a signed zero. Another one is, should we just abandon underflow testing? I mean, should we just abandon it and just say, we're really now in a new era of computation where we want to push the boundaries of performance, and underflow testing is holding us back. Another thing is, I didn't talk about too much, is exceptional cases. So in C, you would have something like 0 to the power of 0 is 1. In Mathematica, you'll get an indeterminate for that. Okay, and that means that just this one value here, we can't use these vector libraries for power because we don't know if our vector is going to contain a 0 or not. So maybe for machine arithmetic, we should have different exceptional cases that match the IEEE arithmetic cases. We say machine arithmetic, to do it fast, you have to match this standard, and maybe we should say that for machine arithmetic, we will adhere to that standard. Another thing is we should look at maybe reviewing some of the auto-simplification rules. And some other things that we're looking at is improving the use of SIMD instructions for vectorization. And of course, the runtime library, that's Abdul. I don't know if you're going to talk about it. Abdul's talk 11:30 later. So he might give you a glimpse of that in his talk. So thank you. Sorry for going on so long.